math and beats. It's that time, and that time is, let's talk about the squeeze theorem for sequences. Let's take a look at it. Squeeze theorem for sequences. What is it? Gonna do a little squeezy. Well, we're gonna consider here, we got three different sequences. A sub k, B sub k, and C sub k. And let's let those three sequences be convergent sequences. All right? With this situation going on right here that I'm boxing in, and that is the explicit formulas C sub k, B sub k, and A sub k have this relationship such that the terms in the sequence C sub k are always the smallest of the terms, with A sub k always being the biggest of the terms, and the terms in B sub k being trapped in between these two different sequences. Of course, they could be the same values as well. And that is true for some situation. Some relevant values such that k is bigger than some number n. Now, since k is taking on values 1, 2, 3, 4, and so on, then what we're saying here is that perhaps we are interested in the limit of these three different sequences. And so maybe these behaviors that we've described in this situation aren't happening. Maybe for the first 50 terms, maybe for the first 5 terms, maybe for the first 100 terms. But eventually, because k is going to infinity and that's what we're interested in, then as long as it happens at some point, some value of k bigger than some other positive integer n, then that's what we're interested in. And as long as that happens, and these conditions are true once that happens, then if we have that the limits as k goes to infinity of A sub k and the limit as k goes to infinity of C sub k is the same limit L, then the limit of B sub k, of course, has to be L as well. This is very, very similar to the squeeze theorem for real valued functions over intervals of real numbers. But now we just have sequences. So there you go. Just to visualize real quick before we look at an example, and that's the end of the video, is, well, we're really talking about something like this. Okay, so we had written above that the sequence C sub k should be less than or equal to the sequence B sub k should be less than or equal to sequence terms A sub k. So in this picture here, we're trying to display such a thing. And because those red dots that you see there are the biggest of the dots vertically across these values of k, that would be our A sub k sequence, the biggest of them all. And then the smallest of them all, C sub k, is the blue sequence that you see down there. Now, that means in our diagram, the sequence, the green one, that's the sequence B sub k. And so what we have here is a graph trying to get across the idea of what this sequence theorem is about, this squeeze theorem. And that is, if we have that situation, again, starting somewhere for k, maybe this is at 500 down here, okay, just pretend. Because we're only interested in the convergence of these sequences, meaning k goes to infinity, then as long as it starts happening somewhere, then we're assuming this situation is happening, okay? So if the sequence A sub k, the red dots, go to some number, whatever it may be, and the blue dots also go to that same number, and the green dots got to be in between the red and the blue dots always, then there's no way that it wouldn't have to go to the same limit. Because why? Because if it didn't, that would mean it'd have to be somehow above A sub k or below C sub k. So it's got to go to the same place, whatever it is, that limit L. Okay, so that's kind of the concept behind this. It's not a proof, but it's getting across the idea. So we're going to use that idea to figure out what's going on with this sequence down here. So we got this example here. Determine the limit of the sequence cosine k over 3 to the k, or state that it diverges. Maybe it doesn't have a limit. Well, The reason why this is a nice example to show why the squeeze theorem would be of use is because the sequence cosine k over 3 to the k doesn't behave and does not allow us to use the other previous properties that we've discussed about limits. And that's because cosine k does not approach a unique real number as k goes to infinity, right? It's just going to be trapped between these different values of 1 and -1. And in the denominator there, 3 to the k is going to go to infinity. So you have numbers going between 1 and -1 and all those in between being divided by some number that's getting enormously large as k goes to infinity. So the way we use the squeeze theorem is we want to try to figure out two different functions that this sequence here is trapped in between, and that those two different functions go to the same limit. So that's what we're going to look at. And it's as follows. We're going to just start with what we know. And we know that cosine k, right, is between 1 and, let me get some more room here. It's between -1 and 1, and that is for all values of k bigger than or equal to 1, where k is an integer. Right? Cosine k doesn't go above 1, doesn't go below -1 ever, no matter what, for all real numbers. So for all positive integers, that's true too. All right. Now, notice 3 to the k is always positive. So I can multiply all the different parts of this inequality by 3 to the k, and I won't have to worry about that expression ever being negative and flipping the inequality signs. So that's what I'm going to write. So if I multiply everything through by 3 to the k, on the bottom, of course, in the denominator, I'm going to get -1 over 3 to the k less than or equal to cosine k over 3 to the k less than or equal to 1 over 3 to the k. And again, that is because 3 to the k is always positive for all real k, hence for all positive integers k as well. So now the whole idea of that is to get the function that we're considering trapped between two other functions, and then hopefully, I mean, all we've written down so far is things that are true that we know. Hopefully, as we let k go to infinity now, we can apply the squeeze theorem. Let's see what happens. Well, as k goes to infinity, -1 over 3 to the k, that's just going to go to 0. 3 to the k gets gigantically large. As k goes to infinity, well, 1 over 3 to the k also goes to 0, right? So, hence, by the squeeze theorem, because we got cosine k over 3 to the k less than or equal to 1 over 3 to the k, and is larger than or equal to -1 over 3 to the k, and then both of those sequences, 1 over 3 to the k and -1 over 3 to the k, they both go to 0 as k goes to infinity. It follows by the Squeeze theorem, we get that cosine k over 3 to the k goes to 0 as k goes to infinity, and hence that is your limit of the sequence. That sequence converges. Very nice. So this isn't always the most efficient method, but it's a nice technique to have in case you're stuck with your limit properties and laws and you're not getting anywhere. This is kind of a way that we can get around it, if we can also, of course, make it happen. But it's a nice little other theorem to be utilized here. So anyways, that's it for the Squeeze Theorem video, and keep on going with these videos. More sequences and eventually series to come. Later.